Good, there they come. All right. Looks right. All right. And that will supposedly start projecting. All right. Our Zoom seems to be baffled by the video change. I'm going to have to stop the Zoom sharing and restart it, I think. Yeah, that's better. Good. All right. Good. And this looks good. And we may get the projector here. We will see. Ah, good. Okay. So I think we're on the road here, which is good because I'm very pleased. I'm now able to demonstrate stuff on Linux Windows that completely matches what we've been doing on Linux. And I added another project, and I'll be adding a few more that you can do to see that, although they're all extra credited projects at this point because I've got enough required projects. But I'm glad to bridge the gap. There used to be a pretty jarring jump in this class from Linux to Windows, where the Linux vulnerabilities go into the binary details of how they work, and the Windows vulnerabilities are much harder to understand because Windows is much more complex. And I've now got another way to bridge that gap. So let me just take a look at the schedule. This is October 27. And we're here. Okay, so, next week, I think I fouled this up. Next week it will be at 1 p.m. I tried to update the schedule. The only reason I have to delay it is for this event, November 10. Okay, so next week we meet at 1 p.m. here. It's November 10 that this class will be at 3 p.m. because I have to be at the invitational competition that's happening before this. So anyway, that's probably the only immediate schedule note. I will update my website again after class. I tried to go, class and I hit the wrong week. Anyway, so let me start with the slides, and I will quickly switch to a demo, which I'm very pleased to have. Let me find them. It is lecture, and we are here at 8B. All right. Okay, so this is the second part of Windows overflows, and the main focus today is going to be on Windows defenses. Let me mute all. And that looks pretty good otherwise, and shove this out of the way as much as possible. All right, and we will proceed. Okay, so we're going to talk about stack protection and then heap overflows, and there are other overflows as well. But the main one is stack overflows that we're going to be doing today. So remember, in Linux, you had GCC, and here's a simple program that we used before. And the point of this program is just that you have a main routine and you have a subroutine, and the subroutine has a buffer overflow. So you can overflow it, and when it tries to return at the end of the subroutine, you can hijack the extended instruction pointer and execute this part that says you win. And in order to make that happen, you have to compile it with fno stack protector, which is one of the things we did there, we did compile it without the F-stack protector switch. It turns out on Linux, the canary stack protector is turned off by default in GCC. It's only there if you turn it on, which is surprising to me, but that's the way it is. So when I compile that program two different ways, the default way and with the stack protector, you can see the one with the protector is 80 bytes bigger, the executable. It has a few more instructions, and you can see them if you use GDB. So let me just do this here. If I open it up here and I SSH into my Linux server, this is Kali Linux, the 32-bit Kali that we're using for almost everything, and make it as big as I can. All right, so if I go into 127 and then take a look, here's these programs. So if I look at pwd.c, It's just what I said. There's a main routine that calls test PW, and then it decides whether you win or fail based on this return value. And it's going to return 0 if you get it right and 1 if you get it wrong, and it's hard to figure out what the right answer is. But this get S doesn't limit the input from the user, so you can overflow the pin and overflow the data structures and eventually change the return pointer. That's the point here. Now, if I do this, you can see that I have the default version here at 15,500 bytes, and this one here at 15,600 bytes. So if I do GDB and disassemble PWD, and I disassemble the test password routine, this is the function header, which you talked about before. The first thing that happens whenever you enter a subroutine is you put the old EBP pointer on the stack, because that's you're making a new, this is how you make a new stack frame. You save the previous EBP, which is the bottom of the calling program's stack frame. Then you move ESP into EBP, so you're beginning a new stack frame on top of the old one at the first unused word. And then you push, then you do a calculation, 24, subtracting it from ESP to make you enough room for the local variables. This is where the compiler decides how big your new stack frame has to be by adding up the size of all the variables and whatever other overhead there is, and deciding that this subroutine only needs 24 hexadecimal bytes of stack, which is 32 plus 4, 36 bytes. So it subtracts that, and now the ESP now points to the top of the new stack frame. Now, this mess here is all the header. That's the prologue, which saves the old stack frame and prepares a new stack frame. Now the function can do all sorts of things in the new stack frame, and at the end, it's going to return. So this is a default prologue. Now I'm just going to leave that up there for comparison and open another window and connect to my server. And we'll do the same thing with the other one. So 127 GDB PWDP. Okay, then disassemble, test. Okay, and I'll make it the same size as much as possible so we can compare these two things. That was the prologue of that function, and this is the new prologue. And let me see if there's any way to get this Zoom junk off the screen. And the so this is the same up to this point, and now it has this matches that. It has added this one line, this call. And what this does, wait, that extunk is also there. Hold on, down here it is, the GS stuff. There we are. So let me shove these around so they're more visible there. That's what I want. So I have push, move, push, then call the thunk, then add something, and then I have this move L, 0xf right here. I went from the add 2e to the move xf. These are the 3 additional lines that were added by the F stack protector switch in compilation. And what this does is it goes to the G segment. Remember, the F segment and the G segment are ways to point to different segments, and I think the G segment is the data segment. It goes to the data segment, offsets by 14 bytes in hexadecimal, and puts that in EAX. Then it loads it to this location, which is 12 bytes above the base pointer. So on the new stack frame, almost at the end, it puts another value, which wasn't stored there before, and that's all it does. Then it clears EAX. This is the stack canary value. The point of this is it fetches a value which is hopefully created randomly and hard for the attacker to find out, and it puts it at the end of the stack frame, and now if you overflow the stack, it'll notice the canary has changed, and when you reach the end of the function, that will prevent it from returning. So if we go down here to the end, here is the unprotected leaving of a function. And let's go take a look at the protected leaving. The protected leaving has this thing. It calls check stack fail. That's the function that checks to see if that canary value has changed. And if it has changed, it's not going to ever execute this return because it's not going to trust the saved instruction pointer anymore. It's going to give me an error message and say, I quit, somebody's been overflowing the stack. That's the point. So let's try it in practice. If I quit here and I run the unprotected function PWD, and then I put in a lot of stuff, I got a segmentation fault. If I run the protected one and feed in exactly the same stuff, it says stack smashing detected, which is different than the operating system just crashing. And see, the reason it gave me a segmentation fault was it proceeded to the step where it tried to use the corrupted instruction pointer. And here it did not proceed there. In fact, I think it would be good to just do this all the way in GDB. Let's enter GDB. And oops, I want to specify the function here. Let's do pwd. And now run. And now enter that password. And it gives me a segmentation fault down here. It crashes. And if I do, I want to see the instruction that caused the crash. Let's try this. I ended up here. It's trying to jump to an address involving BPX. And if I look at my registers, EBX contains letters I put in, 6161. Those are lowercase a's. So it's not as simple as just my numbers ending up in the instruction pointer, but it is trying to jump to an address under my control. And it may just be that I didn't give it enough. Let me try running it again. Let's give it a longer thing in all capital A's. There, that should be enough. Yep, that did it. I happened just by chance to hit one of the overflows that didn't complete filling it. Now if I do info registers, the instruction pointer is this, and that's why it crashed, because that's not a valid address. So this is trivially exploitable. This is what we've been doing. Let's try the other one for comparison, and I'll put it over here to make it easy to flip back and forth. If I quit from here and I GDB the protected one, which is PWDP, and then I run, and then I put in the same thing, it gives me stack smashing detected, and it stops in a kernel call. It never, and if I look at the registers, it did not put capital A's in any of the registers. It didn't let that happen. The whole point of the canary is before it took saved values and put them in the registers and tried to keep going, it detected that that was not going to work and prevented it. So that's the point of canary values. And we can do the same thing on Windows. So let me go back to my slides and see, so we've seen this, that the prologue has new code and the epilogue has new code for each function. So it saves the canary and checks the canary every time, and it makes your function a little bit bigger and a whole lot safer. And it ends this category of buffer overflows. Or to be fair, it makes them more difficult. We will have to use more complex techniques to overcome it. Windows has this turned on by default, unlike Linux. And now, this semester, I learned how to get a small version of Visual Studio running in my other class, and I added this here as an extra credit project. You can now do very comparable compilation in Microsoft Windows, but you have to use Server 2018 and C++. So, but I'm able to compile almost exactly the same program. The only difference is I have to use IOStream and I have to use CIN and COUT instead of gets and puts, because it's C++ instead of C, but the difference is not large. So let me bring this up and we'll look at this in Windows. And it's good to see these tools. So here is Windows. Let me get rid of Ollie. I was just debugging another problem there. And so when you install on Windows the Visual Studio compilation tools, Microsoft used to make you install 5 gigabytes of Visual Studio. Now you can install a much smaller package and just get the ability to command line compile things like GCC. I think it's still 1 gigabyte because Microsoft is always monstrously huge, but it's reasonably possible to do. And what you end up with is you have Visual Studios installed, and if you click Start and go down to V and expand this section, there's a thing called Developer Command Prompt for Visual Studio. So you do that, and now you're going to be able to compile things on the command line in Windows. And again, I'm going to try and make my font big. All right. And so what I did was I just made a folder called 127 in the root of C, and in here I have these programs. And when you're working in Windows, normal people start from the desktop, they go into documents, they make a file and all that. That's the normal Windows flow. What I highly recommend is switching to a flow that will more resemble our Linux flow. So I just work right here and use Notepad instead of Nano. So I Notepad pwd.cpp will let me see it here. And again, I can make the font bigger. There. All right. And it's not necessarily so important to this class, but it's very important for my Python class to get used to doing it this way, because otherwise Microsoft will put your documents in some weird place like C, username documents, and the programs you need are somewhere else. And since open source tools never fix the path, you can't run them from any folder. And fixing the path is fantastically difficult to do on versions of Windows, so it's much easier to just work in one folder. And anyway, so now I'm able to have this program here. When you compile it, the compiling switch is not too baffling. Let me bring it up here. To compile things, you use CL instead of GCC, and this EHSC is something to do with the exception handler, and I haven't really looked into it. I got that from the Microsoft documentation compiled that way. I didn't bother looking any further into it. That was enough, because that's whatever you do to normally compile things. So let's compile this normally, and you do it with this one here. It's probably in my up arrow list. Nope, okay. So it is CL /EHSP, I think. EHSC, okay. And you just give it the name of your file. First, let me remove all my old stuff. I'm going to delete pwdn.star, and then delete pwd.exe, and delete the object. Okay, now if I do dir, the only thing in here is pwd.cpp, which is that notepad file. If I want to compile it, it's CL EHSC, CL/EHSC PW there. Whoops, there, pw.cpp. That's the Microsoft compiler. Very simple. You do not get to choose the output file, or at least you don't have to. So it puts the output in pwd.object for the object file, and then it links and forms the executable file in pwd.exe. And I can run that. And if I put in a password, it says fail. And if I put in a longer password, it gives me an error message telling me it stopped working. And by default, Microsoft does not give me any information about this really. So I don't know, I don't learn much there about why it failed. All right. But if I want to compile it, this is compiled with stack protection. If I want to see the other case, I have to make the one without stack protection. So first I need to make a copy of the source code, although I could in fact recompile the same source code just to make it more clear. I like to make a copy. So let's take pwd.cpp and put it in pwdn.cpp will be the one without the stack protections. And now I'm going to compile it. Oh, that's right, because that's Linux. Yeah, thank you. All right. And it probably didn't put it in the list either. There, it did. Good, thank you. Okay, good. All right. Now, there. So I'm going to compile it, but I'm going to do GS minus S. All right, I got to get the switch again. It's GS minus. Oh, good. Okay. I have no idea what GS stands for. Stack protections in whatever Microsoft terminology is being used here. Okay. And so now I've made PW, and if I do dir, you can compare them. Here is the original one with the protection, 215,552, and the one without the protection is 250,040. So it's smaller because it won't have that extra stuff in the header and the prologue and epilogue of each function. And if I run it though, I won't be able to see any difference here. If I run the unprotected one, and oops, I don't want to do that. I want to run the exe. Okay, now I can put in a password. And again, the default Microsoft error handling does not give me any information. There's no clue here to tell me that in fact it detected a different problem for why it crashed. But if I run it in Anley debug, I'll see the difference. And I think I'll just do that before we proceed. Or not Anley, but immunity. I put immunity on here, which is what I prefer for modern versions of Windows. And it doesn't go into the start menu because Microsoft can't make a search engine, but it is on the desktop. They can't even search their own programs menu because it's a 32-bit program. But it's Microsoft Windows. It now has record profit. They're now number 2 company in the whole world. So I'm clearly in the minority in finding it a hopelessly broken product. But obviously, they're right to make this the way people like products, and I'm just nuts to think they should work differently. Anyway, so here's the one with no protection, PWDN. I wrote it up in immunity, and then I click run to run it, and for some reason it pauses again right away. I don't really know why, but you click run again and now it runs. So there was some kind of, anyway, now it's asking for the password. So I'm going to give it that long password of capital A's and let it crash, and now access violation when executing, 41, 41, 41, 41. This is good, right? We know this is what we like to see. Right there in the instruction pointer is 41, 41, 41, 41. This is what you get for not having stack protections. We can own this program pretty easily, and I'll add that next week. I should have that project ready. We can just do exactly the same owning of this Windows version without the stack protection. But if we load the one with stack protection, we're not going to get away with this. If I open this one, PWD, and it's going to terminate the old one and load the new one, and then I got to run and then run it again to open this window, and now I can put in a long password all full of capital A's. And now it does not put that in the pointer. It just says debug program was unable to process exception. It didn't put junk in any of the registers. It caught me before I did that, and it sets an exception saying you got to quit running, this program is corrupt. And that's what the point of it is. So you see why this is important. And Microsoft is correct to enable it by default, and I'm surprised Linux does not enable it by default. But anyway, then we're going to play some games here to see it, and we'll take a look at IDA free to see the actual code. We could probably see them in Anley as well, but IDA Pro is a better tool for this. Now, I haven't used IDA, I think, in the exploit development class, but we're using it in the malware analysis class, and I threw it in this project. It is one of the standard tools, a good thing for you to know. There are various versions. Here I'm using the one that's completely free, IDA freeware. Which works just fine. So I have to tell it what to open. First, I'll open the one without the protection, PWDN, and just say OK. IDA actually has a lot of work to do. Notice this bar changing colors at the top. It takes a while. It's not really ready until it's done filling that colored bar. It has a lot of work to do to analyze the program. Another irritating thing about IDA, just like, remember, Anley would start and then make, or immunity would start and then make you run twice. IDA also dumps you in some kind of launch program which does not contain any interesting code. And it's hard to find the real program. I don't know why, but it's because there are layers of processing involved in executing something. So there may be a smarter way to do this, but this is the only way I know to do it. I have to find the part of the code that I actually wrote instead of the garbage that Windows produced. And the way I do it is with strings. So you do view, open subviews, strings. And in the strings, you will see things I know about, like enter password and fail. That's the code I want, the code that uses that stuff. If you double click this in the strings window, it will take you to the data section where the string is stored. And here is that string, enter password. If you point over to the right, there's a data xref, and there's an address here. And if you hover over that, it'll pop up a little box showing you the code that uses the string. And if you double click it, you finally get where I want to be, which is the actual assembly code that runs the stuff I wrote in C and not some Windows system thing that was used earlier to launch it. So this is the assembly code that asks me for the password. And this is the prologue. You should look familiar. Push EBP, move EBP to ESP, subtract ESP14H. This is how you make a stack frame. You save the bottom of the old stack frame. You put the top of the old stack on the bottom of the new stack, then you subtract something to make room, and now you have a new stack frame. These three instructions here are part of the making the new stack frame. And then we go right into doing stuff like enter password, take it from the user. There's no protection here. So let's take a look at the other one, and I'm going to open them both at once. I want a second copy of IDA running. Okay, and in the second copy, we're going to look at the one with the protection. So I say okay. It takes a few seconds to process, and then it shows me boring junk I don't care about. I have to do view, open subviews, strings, and double click on the string to get to the good stuff, and then double click on the data xref. And now I've gotten the window that shows me the actual assembly language that does the code I wrote. And I can adjust it on the screen, and with care, I can hopefully make them both visible at the same time. Let's try making this one smaller, and There. That's actually getting pretty good. Okay. And so you see here, it's push EBP, move EBP, ESP. It's lining up line by line, subtract 14. Here it had to subtract 18 because it needs room for the cookie. Then it calls, find the security cookie, put it in EAX here, and then it's going to copy it somewhere. So here's a couple of extra commands about the security cookie, and we'll find the same thing at the end when you return. It, what it does here, it goes through some logic. It decides whether to pass a 1 or a 0 back. So you end up with a series of ifs here, and then it does a return here. But this one, with the protection, let me close these side windows and see if I can, there we are. This one with the protection goes through a similar series of logic, but at the end, it doesn't just return, it calls security check cookie. So this is exactly analogous to Linux. It has a couple extra lines at the start, and it makes the stack bigger to store this cookie. And then at the end, before it does the return, it checks to make sure the cookie is okay. So they've just implemented the same protection. And we'll, in future projects, I'm planning to exploit these and show how it's different. Yeah?
So where do they store the reference cookie where they compare it to?
There's two things. It loaded it from the data second somewhere, which is created by some random process.
So it creates a random number.
Right, it creates a random number.
And it puts it back into the...
It puts it in a data section, then it puts it in there at the head of the function, and at the bottom of the function, it lifts it and compares it to the stored from the data section. So it makes sure that it did not change. So there is another copy somewhere. So one way to attack it would be to find a way to erase that copy, or find a way to read that copy and know what to put in. Those are good attacks. So they make those difficult to do, but that's right. It's never perfect, of course, but it will break all the exploits that don't know how to get around it.
And that could be stored in our data section, but it's right?
Yeah, it's created randomly. Now we'll see.
No, but it's stored in the random access memory.
Yes, it is in RAM because the processor has to get to it to compare it. So it's not like there's no place to put it someplace good like a secure element or something. So it's not a very strong defense in that regard. And you can have exploits that defeat this. But it does mean that the previous generation of exploits are no good, and the modern ones have to have more tricks, and that's all you ever get. Every defense, there's an attack that punches through it, and every attack, there's a defense that will stop it. But this is the one that stopped a whole generation of Stack Overflow attacks. Yeah.
Do you know if IDFRO has the ability to compare to disassembled programs?
That's a good question. I do not know if IDFRO can compare to. I wouldn't be surprised if it could. At least the pay version probably can. I know HXD can on Windows compare raw binaries and show you the difference. And in Linux, you have the diff command that can do it. And in Linux, there's also a bin diff command. And I think I've seen Windows comparable programs. So I think there are programs you can download. One of the popular uses of these is when you get a Microsoft patch, you can totally do a diff against the other one and find out what they did and figure out how to write the virus. And there's blogs on how to do this. And if you're not a red teamer but a blue teamer, there's a similar exercise, which would be very good if we had a little more development in our program. I might be doing this in class. You can write your own patches to patch Windows security flaws. It's not that hard. There's a whole group that does this. They think Microsoft is too slow to make out patches, and they offer unofficial patches to patch things. I forget the name. But you'll see them when there's exciting vulnerabilities that Microsoft doesn't patch. They rise to prominence every few months. We have the unofficial patch you could use. Most people would rather wait for the official patch because God knows what's happening if you put that on. But you can tell there's people like me who are pretty disgusted by Windows and more comfortable with open source. And to them, they would probably rather write their own patch than trust Microsoft. Using Windows, you have to put up with everything Microsoft does to you, and it can be pretty infuriating. But if you aren't a developer, you're willing to put up with all that abuse in return to have someone do the work for you. That is where the sweet spot is for most people. Anyway, so that's what I wanted to show you. That's the simple example you can just work through. And so this thing is called the GS compiler flag. And it's on by default now with Visual C++. And this puts security cookies, is what Microsoft calls them. Linux calls them canaries. It's all the same thing. So this 4-byte word is placed on the stack. And it goes like this. You have your stack frame. You have variables stored up here, like arrays and other variables. Then you put the security cookie in before the saved EBP and the saved return address. And when you're done, before you take the saved EBP and put it back in EBP and the saved return address and put it back in EIP, you check to make sure that security cookie has not changed. And if it has changed, you quit with an exception, and you never do use these values that you can't trust anymore. Yeah.
If you say the GS your Microsoft already put in the protection in. So your GS
They added the protection in server around 2003, and they made it so it's on by default. So what I did was compile with no switches, and I got the protection, and then I compiled with the /GS minus to turn it off. The minus is necessary.
So in here you talk about GS is actually to turn it off.
No, this is what you get if GS is turned off. If GS is turned off, if GS, yeah, the minus removes it, exactly. I know the logical sequence is different. In Linux, I have to turn it on. In Windows, I have to turn it off to make the two cases. All right, so the cookie, here's how it makes it. They take the time, the process ID, the thread ID, another measure of time, and another measure of time and performance count. They just take a lot of numbers they can find that vary a lot and combine them all together with XOR. So the end result is it's not completely random, but it's got 17 bits of randomness, which is not too bad. Of course, if the user could somehow predict this, if the attacker could somehow predict a cookie, then it would defeat this protection. So people have done mathematical simulations and analyses and decided that not all the bits are really random. Some of them are predictable. Some of them are not predictable. So here's the % accuracy. They were able to predict bit 30 with 100% accuracy. By how I think if you would run another process under your control on the same server, was the case, and you get some data from that, then some of these bits can be determined, but some of them can't. See, 50% accuracy means you have no information. And so you see there's about 17 bits here, which they were unable to predict, and the rest they were able to predict. So basically we have a random 17-bit number, and that means we have random numbers of about 100,000 values. This is pretty good because some other parts of Microsoft defenses, like address space layout randomization, actually parts of it are down to only 8 bits of randomness. And if you only have 8 random bits, there's only 256 possible values. So if I just try the attack 200 times, I will get lucky. And here, I'd have to try the attack 100,000 times to get lucky. By the way, that's not necessarily impossible either. There are programs that try over and over and over until they get in, but you know, it's 100,000 is better than 200. A million would be better. You know, it's just a defense of some level. The question is an attacker somehow able to do something to you 100,000 times without you noticing? And sometimes that's possible, but usually you have a network intrusion detection system or something else that would catch you by that time. So, you know, this is like, for example, password hashing. You hash passwords instead of storing them in plain text. So when someone steals them, they have to crack them, and that takes some time. It's not going to keep them out forever, but it's going to keep them out long enough that you can force a password reset. And that's what this is going to do. Slow them down so you hopefully have time to notice some clown is sending an attack 100,000 times at my server. All right, so here's the prologue modification. It takes the security cookie, stored in the data section, and stores it on the stack with this location, including EBP, to put it on the stack someplace. And the epilogue will check, calling security check cookie, just like we saw. So that's the game. If the check fails, it will call a handler, which will not try to return the function. It will just cause an exception, and that'll be the end of that. Now, there's another defense that Microsoft turns on with GS. Before this, data values, local variables, were just put on in the order in which the programmer declared them. But Microsoft decided that it is safer to rearrange them and put the arrays at the bottom, because integer variables are not a risk for buffer overflows, because you can't put more than 4 bytes in the integer, or whatever the size of it is. If you try to put in a big number, it just overflows and becomes a negative number, which is what an integer overflow is, and that might cause a problem, but it does not create this problem where you're overwriting memory location. It does not cause the memory to become corrupt. The only thing that causes the memory to become corrupt is strings, which unfortunately are used in C by storing the pointer and then just adding more data byte after byte beyond that pointer without knowing how far to go. That's the risk. So logically, what you'd want to do is move the strings to the end. So here's what happens in the old system before you have the /GS flag. If I declared them in this order, we just put the name there, the password there, then an integer variable like a Boolean saying whether I'm an administrator would be down here. And see, this means even if I have the security cookie, I can still exploit the program because I can overflow the name and change the value of isAdmin. And the cookie won't detect that if I don't keep going. So I can do something bad even with the cookie protection in place. So to prevent that, they put all the strings down at the end. Now I could still overflow one string into a different string, and that might be bad, but it lowers the attack surface. I have less, yeah.
First on the right.
Yeah.
Versus Boolean.
Yeah, you put everything else that's not a string first, and you put all the strings at the end. So, yep. So they really, so hopefully the strings will hit the cookie before they hit anything important. That's the idea. And they now, if you wanted to be logical about this, you might want to put like a security cookie after each string, so a string can overflow the next string, or after each variable. That might be nice, but they haven't done that. That would probably slow you down a lot, but it'd probably make you safer. And there may be some smart reason not to do it that way. This is as far as they've gone. So here's another picture out, before and after snapshots of the buffer. I think we've already covered this. As you override parameters, you leak. And all right, so we changed the cookie. All right, so here are ways to defeat this protection. And we talked about briefly before. I could somehow rewrite the cookie value in the data section before calling the function. Then it would load a value under my control in there, and I'd know what it should be. Or I could overwrite the handler. This is a security handler, because what it does when the check fails is it calls a security handler like an exception handler. And if I could change that handler or the address to it, I could cause it to fail and then go back and run my code anyway. So those are reasonable ways to do it. You could also just set the handler to an invalid value like 0 and then exploit by altering the exception handler. So your cookie fail will cause an exception, but I control the exception handler and I can now get back into my code. These are ways to get around it. All right, and then there's the heap. That was all the stack. The stack is special because it has the instruction pointer stored right there on the stack. So that's a nice, convenient, juicy target. If you're in the heap, you typically do not have that. You don't normally store register values or addresses that are used to control EIP directly in the heap. Now, the heap is intended to handle chunks of data that keep coming in that of various sizes where you don't have to keep hold of that data forever. So you have data coming in, like HTTP requests. They're all different sizes. What you want to do is store them in a temporary storage in the heap, process them. If you're something like a web server, like Apache, these requests are coming in, you're servicing them. You want to store the request long enough to service it, then throw it away and reuse that memory for the next request. So your server doesn't use all the memory in the server and crash. That's called a RAM leak. If you use memory and then forget to give it back and then use more memory and forget to give it back, Windows 95 had a lot of them, many generations of software had it, where if you just let it run, it'll gradually use up more and more and more RAM until it crashes. So to avoid that, you use the heap. So each process has a process heap, and you can run this C API call, the get process heap, will give you a handle to your process heap, and it's also stored in the process environment block. So here's the assembly language that will get it. It's that FS, in this case, 30 blocks off the FS pointer, and that tells you where the heap is.
Question.
Yeah.
The requesting the handle doesn't create the heap?
No.
Okay.
Yeah, the heap, that's a very good point. The heap is created at compile time. It sets aside room for the heap, and when you use it, you get a hand pointer to it, and then you have to call alloc to allocate space and free to free the space. Absolutely. So a process can create as many heaps as it wants to inside the default process heaps. It's sort of like taking a hard drive and subdividing into like D and E and F. You can subdivide the available heap into as many subheaps as you want, like that. And you'll have a list of the heaps stored and dynamic heaps created, and they ultimately go back to the process environment block, the PEB. So you borrow a chunk of memory on the heap, so your application can have some. And then when you're done, you call heap free or local free or global free in different versions of Windows. So you allocate space. In Linux, it's a malloc and free. In Windows, it's a few different versions of malloc and a few different versions of free, because Windows is a much more complicated beast. All right, so the stack grows downwards. Each new stack frame is up at a lower address. The heap grows upwards. And it has list entry blocks structures. So in general, the heap looks like this. I got this picture from some textbook. The heap is a series of, is a linked list of structures of variable size. You have a node here that stores some data, and then you have a forward pointer and a reverse pointer. The forward pointer points to the start of the next node, and the reverse pointer points back to the previous node. This is an intentional data structure, and the point is you can have arbitrary things of different sizes connected together. So suppose you do free the one in the middle. When you free the one in the middle, you mark this data available, and then you have to update the pointer from the Harry node to point to the Sandman node. So you have to change a forward pointer here, and you have to change a reverse pointer from this one back to skip over that spot. So this means the free command involves two write operations. And the write operations have to write to an address that is in this node and from data that came from the other node. And the point is, if you are able to overflow the data here, you're able to control values here that affect a write operation. And you can control both the address that's written to and the value that's written to it. That's what we typically get with a heap overflow. Yeah.
So the heap free function doesn't do that. The C programmer.
No, the heap free function does update this stuff. But what it doesn't do is know if it's corrupt. So if I am able to overflow Larry and change the values here, then when this attempts to write a new pointer to Susan, it's going to use an address that I could have sent somewhere else. And when it tries to put data there, it's going to use data that I might have corrupted. So I end up, the end result, the natural result of a stack overflow is direct control of EIP. The natural result of a heap overflow is the ability to do one write, where you can write to an address of your choice and you can put in data of your choice. And so you now have to write a byte someplace where it will later control the EIP. Which is not all that difficult, but it is a little more complicated to exploit. All right, and that's the game. And there's in fact much, much more to it. Microsoft has attempts to defrag the heap, attempts to clean up the heap, sub-heaps, a look-aside list. Microsoft has a ton of complicated additional details in the heap, but you don't need to know all that to exploit it, because in the end, you usually get down to one write you control. But if you really get into the nitty-gritty, there are long blog articles and papers about what's really going on in there. And when I always thought Windows heap exploits were so baffling, I'd never go there. But it doesn't turn out to be that hard to do, because you don't really need to understand all that to break it. So you can, once you get that ability to do that right, you could write an exception handler. Then when you trigger an exception, it'll go there. You could overwrite the unhandled exception filter. You could overwrite something in the process environment block that causes it to look somewhere else for pointers later when it needs them. And any of those will give you effectively control of the EIP. Details in Chapter 8. Yes, yeah. Some of those details are in Chapter 8, but not too many, actually. They go into a little bit more than me, but especially, remember, this book is kind of old. So there's even when you understood everything in a chapter, there's like 10 years of more improvements after that. And Microsoft has put a lot of energy in improving the heap. The heap in Windows 10 has a bunch of new defenses. And in Windows Server 2012 and 2012 R2, they added more defenses. It's an area of vigorous exploitation and defense. Anyway, here's other things you can do. You can write in this random critical section that'll eventually end up there. Anyway, all right, in Windows 2003, it doesn't use those, but there are other functions you can exploit. There's quite a few things to play with. And then there's exception handling. And this came out since XP. The exception handler in Windows is a structured exception handler, and you can change it. So in principle, you could override a pointer to the unhandled exception filter, and this would ultimately lead to address you control ending up in the EIP. These are just various vulnerable spots in Windows where you can write and gain control of the machine. If you overflow, you have, of course, corrupted the heap. Now, in Cisco, you couldn't get away with any of this. Cisco routers have a process called check heaps that runs every 2 seconds. And all it does is start at the top of the heap and hop to the next chunk, the next chunk, the next chunk to the end, and then hop back. And if it doesn't make it all the way to the end and make it all the way back, it crashes, says forget everything, kill everything, the heap is corrupt. And Windows has, in fact, been adding defenses similar to that, because that's actually not too hard to do. What you do is you put something at the end, you hop to it, and then hop back and make sure you really got there. Then and if anybody's been corrupting the heap, they're going to break that, unless you write your exploit more carefully to not break the heap. Yeah.
You showed hacker,
Yeah.
Larry's Susan.
Yeah.
So if I go from hacker to Susan and take out Larry, the check heap will still traverse it.
It will, if you fix the pointers correctly. Well, that's what's supposed to happen. You take out the one in the middle, you update the pointers both ways, now you just hop over it. So when I'm overriding it to do my arbitrary write, I'm damaging those pointers. But what I could do is I could overwrite the value run my code, and my code could put the values back in that pointer. So it fixes the heap. And that would work. And that's what you'd have to do. And this is analogous to the much simpler situation we had way back in the first or second demonstration, where we did the overflow from that function to print the uWin message, and then it crashed. And I said, that's because we didn't fix the EBP. We just tramped all over the EBP with capital A's and then put a good value in EIP. If you actually carefully put the valid number back in EBP, you can actually return to the main program and resume without a crash. And it's the same thing here. You could undo the damage you caused by writing a more careful exploit. If we did the same thing when we exploited PuTTY. We had a thing that was supposed to print login as on the screen. We deflected it down to extra code where it ran a shellcode. Well, we could have made it launch a new process as a shellcode and then come back and print the message so the user could keep using PuTTY and not know they just got owned. And that would be a superior exploit. Anyway, it's the same thing here. By the way, they said the simplest repair process, rather than trying to figure out how to fix all the pointers, would be to just erase the heap. But then it's valid again. You lose the data on the heap, it will pass your heap integrity check. Something else will crash later because the data that should be on the heap isn't there, but you know, you make it a little further. All right, to restore the exception, if you change the exception handler, your handler should change it back. Otherwise, the next exception will cause a crash. You know, there's just different levels of exploits. This is why, you know, script kiddies start with DOS exploits to crash the server, and the more cool you get, the more beautiful you are. Diving in with no ripple where you don't crash anything, it still works. You don't hog up a lot of memory. You don't trigger a lot of warnings. And the IDS, you know, that's the pro, where you become delicate like a rapier. You strike what you want without hurting a lot of collateral damage. That's right. That's right. Or a brick thrower. We're hopefully, this class is hopefully taking you beyond throwing bricks in the window up to, like, you know, prying it open with a crowbar. But we're not getting all the way up to the grays that just come and go and you never knew they were there. That's really cool, but we're not getting there. All right, so then there's component object models. These are models, data structures with attributes and methods that are created on the heap, and they have code in them, and there's a bunch of them. And there's a table called the V table that points to these things. These things are, the COM object model is a big part of Windows, and they contain data, and those data fields can overflow. And they can even overflow into the next object's V table. So you can have a overflow of COM objects that changes the address for other COM objects, very much like a heap overflow. It turns out that there are a ton of these things. They stay in Windows forever, and they are not removed when they are found to have vulnerabilities. They're just added to a kill bit list. And one attack is to overcome the kill bit list. There was another similar defense in a technology which I think is now finally dead called ActiveX that Microsoft wrote, which was a pretty horrible idea from the start. The idea was to run precompiled code in the browser. And Microsoft rapidly discovered that this is very dangerous. You can format C, send out emails, do anything you want from the browser. And so then they started marking Microsoft extensions as safe to run in ActiveX, but it was just a flag. So you could make other ActiveX extensions that said they were safe to run, but weren't safe to run. They often have defenses like this. So anyway, now they have a kill bit. And I went and found a tool called Ole COM Object Viewer to run. And I ran it on, I think, Windows 7. And lots of these things are loaded on your machine. These things sort of accumulate like barnacles in Windows. More and more of these strange bits of code. Yeah.
You're saying there's code they never use, it's still on the operating system.
Tons of it.
But instead of removing it,
yes,
you have a list somewhere that says just don't run it.
That's exactly right.
Okay.
That's why Microsoft, see, the thing you understand about Windows is like the Frankenstein monster. Microsoft doesn't actually write the code. What they do is buy up companies and then patch it in, like sewing in the leg from this guy and the arm from this guy. And they imperfectly patch it in, and that's Windows. And there's also a lot of old stuff, and it's really, really hard for them to determine if that old stuff is still in use. So they're real reluctant to remove it.
Can you edit the kill list?
Yes. Okay. That's one form of attack. You can edit the kill list to turn this stuff back on. You know, there's a bunch of holes because it is a huge, the fundamental logical problem is that Windows is the all-purpose operating system. Whether you want a cash register or an airplane or a nuclear control plant or a bomber, it's all running the same thing because it's the all-purpose operating system. And the Linux people are like, oh, you should never even think this way. You should have a different OS for each purpose. And they're like, this would be so much cheaper And they're making piles of money. It's so much easier to just use Windows. You can just get developers that have been trained and all the tools are right there. It's so much easier than using Linux where they actually have to know this particular task. So, Windows, it's a lot of purists, like mathematics would say, you never use Windows. Windows is horrible, but it is usually the cheapest, easiest way to get whatever you're doing done is to just do it on Windows. As long as you don't mind carrying around a whole bunch of extra junk you're not using. And typically, that isn't very expensive, so that's what people do. Anyway, there are other things you can overflow. You could overflow in the data section itself. You could have a buffer in the data section and something after it. You could overflow this onto the next one with glorious C and C++ and everything. Don't check for that either. You could, in principle, overflow buffers in the thread environment block. And then you could change pointers, although this is just a theoretical attack. At least at the time of your book, this hasn't actually been done. Yeah.
Can you go back to the
Yeah.
Is this the issue of like the order you put it in?
Well, yes. Well, you could, the order might help, but this is not in a subroutine. These are global variables outside the subroutine. That's what goes in the data section. They're not in the code section at all. They're not on the stack, and they're not in the heap. But they're still handled by C, so in principle, you could overflow. Yeah, that's all. And in principle, you could overflow them too, but at least as of the time of your book, nobody had actually done that. And I got a few cahoots about this stuff, and then I'll point you to the next project, although I may not go through it all today. Let's take a look. We got cahoots, which are here, and they should be my favorites. There we go. 8B is here. Okay. It's a similar thing, by the way, with drivers. Windows has thousands of drivers for hardware you're not using. That's why the purists use something like Arch Linux that doesn't have anything you're not using, therefore much smaller and faster. But most people don't care about a little wasted space on the hard drive and wasted RAM. They just want it to be easier to use. So I can just plug in something and have it run. I don't have to recompile the kernel for 36 hours because I'm plugging in a different device. All right, I'll wait a while. Gives me enough time to optimize the sound quality. Somebody told me that the professional videos they make over there, they cut through the Kahoot time to make it snappier. That's pretty, I didn't slide face. When you're waiting for 20 seconds, they just go zoop. That's what you get for professional editing. Now, you do miss the tune, I guess, yes, yeah, well, yeah, I know, I feel that way, but maybe I'm just conditioned to love my slavery, and I don't know the joy I would have by being freed from it. Anyway. Yeah, but here we are like driving to school to sit in the classroom, we're like the old school people. But I've taken online courses and I really don't like them much. I mean, make it available for people who prefer it, but I'd rather really go to class. What's that? Yeah, I mean, certainly online is an option, but I'd rather really go to class. All right, I guess I got everyone we're going to get. Let's do it. All right, so which one is a canary? Okay, that's it, a security cookie. All right. So which one is used by most Windows API functions? Oh boy. Well, as far as go by, and I do not remember it. Well, they all have process heaps. I knew that. I thought it might be which one of those particular allocation functions they use, but they all have process heaps. That's a fair statement. Anyway, all right, where's the kill bit? Which one has this crazy kill bit list? Yep, those COM objects, which were a few chapters back, the brilliance and idiocy of the Microsoft DCOM model. The whole thing about Microsoft is you can keep reusing legacy code forever in more and more complicated environments that was never intended for. That is incredibly stupid or incredibly brilliant. And I'd say from the stock market, incredibly brilliant is winning over incredibly stupid. Microsoft's making record profits with this philosophy, which is that making more money is more important than some theoretical security idea. That does appear to be the winning formula. That's pretty American too. You know, if you had enough money, you could laugh at the security problems. Anyway, so, all right. Which API call is most likely to be exploitable by Heap overflow? That's a fair one. All right, this one is doable. This one gets the handle to a heap, which is not dangerous at all. This one creates a heap section for you to use. Heap create, heap allocate, allocates a piece of space for you to use. None of those are dangerous. The dangerous one is free, which involves writing these pointers and using data that came from other chunks of the heap, which might have had an error. So it's the same as Linux. The free point is the most likely point of exploitation. Anyway, all right. And which one is created when needed by another program? Yeah, they're COM objects. They're like services that start when needed. They're available, just like drivers are available. They don't load them until you plug in that device. The COM objects are available, and when a program asks them, they load up. Anyway, that's the dramatic world of Windows madness. And I'm going to make note. I got MDOT. I know who that is. I know who Peter D is, but I don't know who Big D is. So Big D is going to have to give me more information if they want to get their points. Anyway, let me save this someplace. And let me see if there's anything I should say about the project. So the project that I did today was the latest one, 13X, where you do stack protection. And I'll probably follow it with the 14X, where we now exploit this vulnerable code that matches what we had way back in the Linux project, like 2 or 3. And as far as exploiting vulnerable servers, the big one, there's one here with easy RM MP3 converter, which is one of the things people did. This thing is a file converter. These things are frequently exploited, like unzip utilities are frequently exploited. So here's an application you can get from an old exploit database. You're getting an old version. This will convert a media file. And this is nice to see Windows. The principle is just the same as Linux. In practice, there's a few differences. It turns out it has to be really long. So the attack is not sent over the network. You have to make a fuzzer that prints a bunch of junk and then put it in a file called M3U and then put it on Windows and try to convert it with the converter. So you load a playlist and you put the M3U file in. This is how you do it. So it tries to play that MP3 file, which is just full of A's. And when you do, it gives you an error message saying failure in loading file because this file is just full of junk. And it looks like it read this as the file name. So the file name contained 10,000 A's. This, by the way, was true of Chrome. The first version of Chrome had a very simple exploit. All you had to do was to save a web page and put more than 100 characters in the file name. It would overflow and crash. So whenever they reserved space for the file name, they didn't think of this. So now, if you put in 20,000 and 30,000, you will find that 30,000 actually crash it. So 30,000 in whatever space they allocated for file name is enough to crash it, and now you just have to exploit it. So you can observe it in immunity, watch it crash, and you'll see 41, 41, 41, 41 right in the EIP. Same old stuff. This is gristle for our mill. So now you know this game. You can restart the thing. Now create a non-repeating pattern of characters for the last 10,000, because you know 20,000 didn't crash it and 30,000 did. So somewhere in the last 10,000 characters is the EIP. So put that junk in. And now when you've done that, it will crash with a pattern here, 250, whatever 50 is, the 16th letter in the alphabet. Then that twice 2PP2 or something of that sort. 2PP2. So you can find out where 2PP2 is in the pattern, and that tells you where it is. And so now it is you can now target the EIP precisely for putting the right amount of data here with BCDE. This is all following exactly the same pattern we've done many times. When you get it right, you'll get BCDE here. So now you control the EIP exactly. Now all you have to do is put in an exploit and run it. You can examine memory at ESP. And if you examine, you'll find these Fs that you put in. Now this exploit is following the same pattern as the one in the previous one. I put in A's, then the BCDE for the EIP, and after that I put in Fs, just for this reason, so I can look and see where data I see in RAM is in my exploit. And I see that the stack is full of Fs. And if I scroll up one line, I'll see that it's in fact pointing to an F just after the first 4 Fs. So here was my EIP. Then there's 4 Fs, which ended up somewhere I don't care about. And then ESP points here. So if I start my exploit here, I can get there with a jump ESP, just like we did in the previous one. So list modules with Mona. Find a module that doesn't move, and you will find that the MSRM filter 03.dil is the module that has this property. It's this one right on top, and each time I start it, it does not move. And it's loaded at this base address of 10000, so the address does not contain leading zeros. So addresses in the middle of this will not have a 0 in them, because null bytes are bad, and it's not going to be moving around. ASLR is turned off. It does not have DX turned on, a DEP. So if I inject code, it will run right there in the buffer. So this is an easy case. All I need to do is find a jump ESP, and here's a Mona command that will find a jump ESP in there. And it found 1. There is 1 occurrence of jump ESP, and it is at an address that doesn't have an embedded 0 because it goes like this: 1001 B058. There are 2 zeros, but there's not a null byte. So I can use that address. 1 is all I need. So now I can put a NOP sled in and inject that address. And if it works, it will run down my NOP sled. And that's what happened when I run it. It hits the int3 command. So it went here and it went nop, 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 int. So my NOP's executed. That means anything I put there will execute. So now I can just go to, I got to find the bad characters, the usual way. And then I can go to Linux, make an attack file with MSF Venom, as we've done before. I made a reverse shell again because that's the one you usually use on Windows, because the Windows default firewall blocks any ports you're not needing. So it usually listening shells won't work. And again, you can send that and get a shell on your Windows machine. And so you run a listener on port 443 and you will get now a command shell on Windows. In this case, I did not use a meterpreter shell. I used a command shell for no particular reason. But here I just used a plain shell reverse TCP instead of a meterpreter reverse shell. So I got a command prompt instead of a meterpreter shell. You could run other attacks too, and it would be all right. But that's the game. This is a good process to practice. There's no chat message here. It might just be identifying someone. Let's see what it says here. Chat, here chat, come back. Okay. Okay, good, a name, okay. All right, I will make a note of that name. All right, good, thank you. And I think that's it. That's your next project, and you got this extra credit one here. There'll be another one coming. Any questions about anything? All right, I'll stop the share and I'll go to the lab, help anybody who wants to work there. Next week, we're meeting at 1. The week after, we meet at 3, because there's a contest. And if anybody wants to come in the morning to join us at the contest, you're welcome. Even before then, our practice sessions are getting well organized, and we can have strangers come in from the program who have not been taking a class. That's fine, because what the students are doing is they are writing instructions to explain to someone how to do it. And if you haven't done it and you have to try following their instructions, that is a beneficial thing for them to practice seeing how good their instructions are. We're trying to develop a playbook to carry to the competition that shows you, reminds you what to do. And it would be good to have people come join us to give feedback and help write more clear instructions. All right. Oh, another chat message coming in. Is it possible to schedule a Skype office hour? Well, I suppose I could. Well, sure. For the moment, just send an email to where the homework goes. And we'll talk to my grader. I can work that out, yeah. All right. I'm stopping this for now.